In this example, we will solve the discontinuous differential equation in the initial value problem y double prime plus 6y prime plus 25y equals delta of t minus 2, with y of 0 equals 0 and y prime of 0 equals 0. Since this is a discontinuous function involved in our differential equation, our only method that will work here is to take the Laplace transform. Taking the Laplace transform of both sides gives us Laplace of y double prime plus 6y prime plus 25y equals the Laplace transform of delta of t minus 2, which we found to be e to the negative 2s. The left-hand side we can split up using linearity as the Laplace of y double prime plus 6 times the Laplace of y prime plus 25 times the Laplace of y. And we found that the Laplace of y double prime is s squared times the Laplace of y minus s times y at 0, which is 0 here, minus y prime at 0, which is also 0. Similarly, we can rewrite the Laplace of y prime as s times the Laplace of y minus y of 0, which again is 0. Now cleaning up this equation, we have s squared times the Laplace of y plus 6s times the Laplace of y plus 25 times the Laplace of y equals e to the negative 2s. And to solve for the Laplace of y, we'll start by factoring out Laplace of y on the left-hand side. And we'll have s squared plus 6s plus 25 all times the Laplace of y equals e to the negative 2s. So now we will need to find the Laplace inverse of the Laplace of y, which is given by e to the negative 2s times 1 over s squared plus 6s plus 25, by dividing our above equation by our coefficient s squared plus 6s plus 25 of the Laplace of y. Seeing that we have a factor of e to the negative 2s tells us that to find the Laplace inverse from here, we'll need to use that the Laplace inverse of e to the negative sc, where c equals 2 here, times the Laplace transform of some function f of t is the shifted function u sub c of t times f evaluated at t minus c, where here the Laplace of f of t is given by 1 over s squared plus 6s plus 25. So we'll need to find f of t, which is the Laplace inverse of that. Since we can't factor s squared plus 6s plus 25, we will need to put it in vertex form. If you'd like to see the steps of that done out, you can click on the pink link. Putting s squared plus 6s plus 25 in vertex form yields that it is s plus 3 all squared plus 16. So we can rewrite the Laplace of y as e to the negative 2s times 1 over s plus 3 squared plus 16. Now that we have it in vertex form, we will need to use a shifted Laplace transform of the sine of alpha of t, which is given by alpha over s squared plus alpha squared. Looking at our denominator here of s plus 3 squared plus 16, we can see that alpha is the square root of 16, or 4. So we'll rewrite this as e to the negative 2s times 1 over s plus 3 squared plus 4 squared. To get this directly in the form alpha over s squared plus alpha squared, we need the numerator, which is now 1, to be 4 as well. To get this, we'll multiply by 4 and 1/4, which won't change the value, just how it's written. So we can rewrite this as e to the negative 2s plus 1/4 times 4 over s plus 3 squared plus 4 squared. Now, with 4 over s plus 3 squared plus 4 squared, we really have a shifted form of the Laplace transform of sine 4t. Since the Laplace transform is shifted here, which we can see from s plus 3, we have that 4 over s plus 3 squared plus 4 squared is the Laplace transform of e to the negative 3t times sine of 4t. So now we have found the function f of t that is the Laplace inverse of 1 over s squared plus 6s plus 25. It's 1/4 times e to the negative 3t times sine of 4t. And now we can use that the Laplace inverse of e to the negative sc times the Laplace transform of f of t is given by the shifted step function u sub c of t times f of t minus c, where here, again, c equals 2. So the Laplace inverse of 1/4 e to the negative 2s times the Laplace transform of e to the negative 3t times sine of 4t is y equals 1/4 u sub 2 of t times the function e to the negative 3 times t minus 2 times sine of 4 times t minus 2. Before ending this video, I would like to make an observation about the solution that we found. Notice that our initial value problem had the outside forcing function delta of t minus 2. This is an impulse function that happens right at the moment t equals 2. However, our solution is given by the shifted step function in terms of u sub 2 of t. The reason for this is that while the impulse only happens at t equals 2, the solution is affected for it from the time t equals 2 on to infinity. In general, differential equations that involve impulse functions will have their solutions involve a step function,